Hi guys, I'm Scott. This is the third episode of QB in the group, and we will introduce some basic concepts about permutations and their mathematical representations. Before that, let's review some basic knowledge of groups at the end of the last video. Here we are to determine whether these four operations upon the sets can form groups. First, for the plus operation on all integers, there is a group structure because we can find 0 as the identity element, and for every element in Z, minus A is also in Z. And for the multiplication operation on all positive rational numbers, the identity element is 1 and the inverse of a is just 1 over a. But multiplication upon all integers d and all rational numbers q cannot establish a group structure, because there isn't an inverse of 0 under multiplication. Therefore, we must carefully check that a group structure satisfies the four axioms: closure, associativity, identity, and inverse, especially the inverse, as it makes a claim about all elements in the set. And now let's come back to the cube. At first, we've learned about some basic operations on the cube, for example, r, which is turning the rightmost layer clockwise by 90 degrees. But now we want to see things from a smaller perspective by just considering each cubie and its displacement during an operation. And for r, let's first discuss the corner cubies, denoted in 1, 2, 3, and 4. During an r operation, 1 goes to the position of 2, 2 goes to 3, 3 goes to 4, and 4 goes back to 1. The similar cycle happens for the edge cubies. 5 goes to 6, 6 goes to 7, 7 goes to 8, and 8 goes back to 5. Now we use some arrows to denote the cycle. For the corner cubie it's 1, 2, 3, 4, 1, and for the edge cubies it's 5, 6, 7, 8, 5. The only cubie that doesn't move is the center cubie. We can actually notice that no matter which basic operation you do on the cubie, the position of the center cubie will not change. Therefore, we can break down the R operation into two cycles, and we can denote them in brackets. Note that this bracket is not what we put operations into. Rather, it is a mathematical language that separates different cycles within a permutation. And by putting these two cycles together, we can write R equals to bracket 1, 2, 3, 4, bracket 5, 6, 7, 8. Now I want to clarify that the cycle notation we've created above is not the only way to denote the permutation. Another way that is shown in various math books is to write the original value and the final value of an element into the big bracket, with the final value on the bottom. Or we can understand this as a function, sigma, that sends 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. The cycle notation is shorter in length, but sometimes, as we'll see soon, is less straightforward. But one benefit of the cycle notation is that it extracts a similar structure from permutation for analysis, such as how we extract a group structure from various number systems. But before that, we want to introduce a basic theorem of permutation. The disjoint cycle is crucial when we start to face more complicated products of cycles. For example, when we denote R as bracket 1, 2, 3, 4, bracket 5, 6, 7, 8, elements in different brackets don't overlap, and that's why we call the cycles as disjoint. But for the next permutation on the screen, P equals to bracket 1 to 3, bracket 1, 3, there is some overlapping elements, and to simplify those complicated notations, we first want to convince ourselves that a disjoint cycle notation exists for all permutations. And this is not very hard to describe, and we'll sketch the informal proof here. But you can search for a formal proof about a further claim. Every permutation can be uniquely written as products of disjoint cycles. Consider a permutation sigma on the screen. We first pick the element 1 and see where it goes. First 1 goes to 3, and 3 goes to 1. So there's a cycle bracket 1, 3. And next we find 2 and see where it goes. 2 goes to 5, 5 goes to 6, and 6 goes back to 2. So there is a cycle of bracket 2, 5, 6. And we skip 3 because we've already included 3 in the first cycle. Then we apply the similar process on 4, and there's a cycle of bracket 4, 7. 8 isn't changed by the permutation, so we simply write bracket 8. And therefore, we can multiply the cycles together to notate sigma, which is sigma equals to bracket 1, 3, bracket 2, 5, 6, bracket 4, 7, bracket 8. The process is just filtering out the related elements together and putting them together. and more rigorously, this notation is called the canonical cycle notation, and you can find the formal proof in this website. But before that, I think we should define what a product of cycle actually is. Because we have only encountered the disjoint cycles before, it's very natural to write the cycles together in the orders. But consider the case when p equals to bracket 1, 2, 3, bracket 1, 3. How can we compute the cycle? The rule is to choose an element from the rightmost cycle, calculate its destination on that cycle, and then continue the process from right to left. To illustrate the concept more vividly, let's draw 3 parking lots, respectively in blue, red, and yellow, and 3 cars in black. We want each car to find its correct parking lot after the permutation, which is the displacement of the car. Let's look at car 1 first. On the rightmost cycle, car 1 goes to parking lot 3 from parking lot 1. Then we notice the leftmost cycle, which is bracket 1 to 3, and sends 3 back to 1. Therefore, since our car parks at 3, it will then go to 1 according to this cycle and stop there because it has completed all the cycles. Similarly, for the second car, the rightmost cycle doesn't do anything on it, so we look at the first cycle and sends 2 to 3. Finally, for the third car, it goes from 3 to 1 in the rightmost cycle, and then on the left cycle it will go to 2 and stops here. Then we can again use arrows to represent the route of the cars as 1 to 3 to 1, 2 to 3, and 3 to 2. Now let's ignore the process and only look at the outcome, and we can rename the parking lot depending on which car parks on it. The original parking lot 2 becomes 3 because car number 3 parks on it, and similarly the original parking lot 3 becomes 2. Looking at the names of a parking lot, we find 2 and 3 switch their tags while 1 doesn't change, and therefore we can write the cycle as bracket 1, bracket 2, 3, which is now a disjoint cycle. And let's look at one more example, and consider the product bracket 1, 2, bracket 2, 3, bracket 3, 4. We start at the rightmost cycle and sends 3 to 4, and stops. Next, we send 4 to 3, and go back 1 cycle and send 3 to 2, and go back to 1 cycle to send 2 to 1. And therefore, 4 goes a long way to 1. There we are done with the rightmost cycle. Now we move to the middle cycle and send 2 to 3, and then we move to the first cycle and send 1 to 2. To summarize, the canonical cycle notation of a product is just bracket 1, 2, 3, 4. And fun facts about this kind of products. It's all made of cycles of 2 elements, which are called transpositions. Actually, we'll see that any permutation can be written as products of transposition, and we will also explore that in our next video. But here you'll find some clues to find out why it is true. Finally, we'll introduce another feature of a permutation, order. The order of a permutation, or P, is the number of times to repeat the permutation until it's undone. In a group notation, it's P to the power of order of P equals to E, which is the identity. And here are some more examples. The order of bracket 1 is just 1, while the order of bracket 1, 2, 3, 4 is 4. If there are several cycles on the canonical cycle notation, then the order is the least common multiplier, LCM, of the respective order. For example, the order of bracket 1 to 3 times bracket 4, 5 is 6, which is the least common multiplier of 3 and 2. And finally, for a notation that is not disjoint, we'd better convert it to the canonical cycle notation to find its order. Thank you for watching Cube in the Group episode 3. In the next episode of this series, we'll explore more about a parity of permutations to resolve some fun questions on the Rubik's Cube. See you next time.